Okay, hello dear students. This is our fourth lecture on heat treatment processes and the third one on various type of annealing processes. In the previous two lectures on annealing, we discussed full annealing. We have also discussed what is called spheroidization annealing, and we have also discussed isothermal annealing. In today's online lecture class, we will discuss two more annealing processes. One is called diffusion annealing or homogenization annealing, and the other is called stress relieving annealing. So let us see the table of contents. The first type of annealing that I'll take is homogenization annealing, or what is also called diffusion annealing. And the last type of annealing that we like to discuss in these classes is called stress relieving annealing. So the objective of each of these processes, the processing route that is followed for these processes, and some other aspects of them would be discussed in today's class. We start with what is called homogenizing annealing or diffusion annealing. Students, you would have heard about a defect called coring. Coring is also called interdendritic segregation. It is also known as enveloping or developing or surrounding, but the most popularly used name for the defect is coring. Now, what does coring mean? Coring means that when you look into the microstructure of a materials system, the chemical composition is not uniform throughout. Means when you look into the different grains of the microstructure, when you look into the different phases which are there in the microstructure, the phases, the grains are not completely uniform in their chemical composition, and the grains are segregated into two regions of high melting point constituents, and there are another regions which are of low melting point constituents. For example, here I have shown a very crude schematic of one steel whose microstructure is suffering from this coring defect. So this complete grain, students, should have been uniform in its chemical composition. But what I have tried to show is that this complete grain does not have uniform chemical composition throughout. Rather, there is this outer region, which I call region close to the grain boundaries, because this region is close to the grain boundaries, or these are interdendritic regions or outer fringes of the microstructure. So this is a region which would have some particular type of a composition, and the central portion of each grain, as I have shown through this green, this would have another type of composition. What experience tells us is that out of all the constituents which are making up your material system, the constituents which have relatively higher melting point, they make up the central portion or the core of the grains. And this outer fringing area or areas near the grain boundaries, here the lower melting point constituents are more concentrated. So if you had taken any composition of the steel, you should have, and there are some phases that have got formulated in the steel. All phases, all grains should have been of some specific composition, and that should have been uniform throughout. But because of this coring defect, and this coring effect happens because of lack of diffusion, which was not able to complete in the material system because of faster cooling. So if chemical composition is not uniform, mechanical properties are not uniform, and a true alloy does not get formed. So ultimately, the material will not have good mechanical properties. The material will have varying properties. It would not be of use. Particularly, students, in case of steels, if you have taken ingots, steels in the form of ingots, the basic raw form in which the steels are manufactured, and if there is a heavy plain carbon steel casting, or if there is a highly alloyed steel casting, during their cooling, diffusion generally is not able to complete, right? And coring occurs. This non-uniformity in chemical composition occurs, because of which mechanical properties are not good, and you need to rectify or improve this microstructure, refine this microstructure, and this is done through homogenizing annealing, or what is called diffusion annealing. Homogenizing, because we will try to homogenize the microstructure which has become heterogeneous in terms of chemical composition. And why diffusion annealing? Because what we will try to do in the steel during the diffusion annealing processes, we'll get diffusion to get completed, and all segregated zones would be eliminated by the diffusion process, and ultimately what you'll get at the room temperature will have all coring, all segregated zones eliminated, and the chemical composition throughout the microstructure, means every phase, every grain, whatever composition it had to had, it would be uniform in its chemical composition. So that's the purpose why homogenization annealing is given. Again, I repeat, this problem is generally noted for steels in case of ingots, in case of heavy castings, in case of highly alloyed castings, and this problem must be eliminated. Let's see how diffusion annealing works. What is the processing route that you have to follow in order to give diffusion annealing to a steel component? See students, this is the only process where you will take your steel from the room temperature to a heat treatment temperature, and that heat treatment temperature, students, will be far in excess of the upper critical temperature. So generally all heat treatment processes complete at about 20 to 40 to 50 degrees above the upper critical temperature, at 850, 900, maximum 950. But in this treatment, because coring has occurred in the steel, segregated zones are there, heavy diffusion is required to eliminate those segregated zones. We have to choose a heat treatment temperature far in excess of the upper critical temperature, and this is generally in the range of 1150 to 1200 degrees centigrade, which is very unusual, which is unexpectedly high. We generally don't hear these type of high temperatures during heat treatment. As I said, we are restricted to somewhere around 850, 900, 950 at the maximum, and we are done with all type of heat treatment processes. But diffusion annealing, because of this problem of coring, we have to go to temperatures as high as 1200 degrees centigrade. Then soaking is also pretty long. You can see 10 to 20 hours of soaking is required at such high temperatures. And finally, slow cooling, because this is annealing, some slow cooling will have to be done. So equilibrium cooling will be done from this high temperature till a temperature that transformation of austenite in whatever phases you wished it to be is complete. Generally, it would be coarse lamellar perlitic structure. From the CCT diagram, you can see at what temperature and with what amount of time passed this transformation would be complete. No sooner austenite decomposition, austenite transformation is complete, no point in sticking to such a slow equilibrium cooling rate. You can follow slightly faster rates of cooling, and you can do air cooling, what we have mentioned over here. You come to the room temperature. As you come to the room temperature, you realize that enough of diffusion has occurred in my steel, and any coring, any interdendritic zones which were having different chemical compositions, by virtue of diffusion now taking place because of these high temperatures and long holding periods of time, diffusion completely takes place in this process and eliminates the coring defect. So this is the procedure that is followed for diffusion annealing. Now let us see that what are the limitations of this process. So students, see, I said very, very high temperatures, heat treatment temperatures have to be followed during diffusion annealing or homogenization annealing. Not only that, at these high temperatures, you have to hold the steel for prolonged periods of time as large as 20 hours. And finally, you have to slowly cool the steel right from that high temperature, still a temperature, till austenite transformation is complete. Because of all these reasons, students, excessive coarsening of the grains will take place. So the final microstructure that you will get after diffusion annealing process would be free from coring, but it would have all other type of problems in it. Number one, because of this high temperature, prolonged holding, slow cooling, excessively coarse grains would be formulated in the room temperature microstructure of the steel. Not only that, uh, materials loss in the form of scales takes place because of subjecting the steel to such high temperature for such long periods of time, followed by slow cooling. So because you have to take the steel to a very high temperature, one second, because you have to take the steel to a very high temperature, you have to hold the steel at this high temperature for a very long of period of time, and then you have to equilibriumly cool the steel for some till some drop in temperature. This is a very costly process. Secondly, because of exposure to such high temperatures for such prolonged holding periods, for such slow cooling, grain coarsening, students, takes place. And if grain coarsening has occurred, means this type of a grain structure with very coarse grains would be seen. Mechanical properties come with fine grains present in the microstructure. So if excessive coarse grain coarsening has taken, you always will have to subject your steel to a subsequent treatment after diffusion annealing has been given. So either you'll give plastic deformation to your steel, or you'll give normalizing heat treatment to your steel which has received diffusion annealing. And why are you giving this second treatment to your steel specimen? Coring got eliminated, but because of grain coarsening, the mechanical properties came down. To restore them, you again subject them to a subsequent treatment after diffusion annealing. Not only this, as I said a while ago, because of the very high temperatures that are involved during diffusion annealing and the large soaking periods that are involved during solution annealing, thick scales are formed on the surface of the steel which result in loss of material. So students, what's the conclusion? The conclusion is that if you do not have a choice for any other heat treatment to eliminate coring, you should do diffusion annealing. Otherwise, it is a very costly process, both because of the high temperatures, the long soaking periods, the equilibrium slow cooling rates, the loss of material because of formation of thick scales, requirement of a secondary heat treatment to refine the grain structure. This, you must avoid this. But if coring has gone to such an extent that coring problem cannot be eliminated by normalizing or by full annealing or by isothermal annealing, and the only choice left is diffusion annealing, then it has to be given. You do not have any choice. You cannot scrap the steel material. You will have to restore it by any means. Then diffusion annealing can be given, but don't give it otherwise. Don't take it, don't do diffusion annealing as a routine exercise, right? Only under very special circumstances we can resort to diffusion annealing. Then we come to the last annealing process that we like to discuss in the class, stress relieving annealing. What is the purpose? As the name only indicates, the purpose of this heat treatment is to eliminate any internal stresses present in the steel. So for any reason, if steel contains what are called internal stresses in it, which are also called residual stresses, or they are also called locked in stresses, then just if the purpose is to eliminate the internal stresses and there is no other problem in the steel component, the choice always is stress relieving annealing. But before I discuss the procedure of this annealing process with you, we must know what is meant by this term internal stresses. So as I said, these stresses are also called residual stresses or locked in stresses. And what are these? See, if there are stresses present in a material, even when there is no external load or force being applied on the material is said to be containing internal stresses. I repeat, generally stress comes in a material when you load it, when you put a force or a load on it. But if you see that there is no external loading or force being applied onto a material, onto a component, still there are some internal stresses present in it, which can be which you can observe through XRD analysis, and there are other quantitative techniques through which we can come to know whether some residual stresses are present in a steel or not. But the point is that without any external loading, still if a material is giving evidence that there are certain stresses present in me, those stresses are internal stresses, residual stresses, locked in stresses. Now students, these are okay. Why do they get generated? Literature says that whenever you will do non-uniform heating, means you'll heat the component, but the heating rate that is being followed is not very uniform. It keeps on varying. Similarly, during equilibrium cooling, the heating rate was not constant. It kept on varying, and importantly, it was non-equilibrium cooling rate. Locked in stresses will get trapped in a steel component. So among other reasons, uneven heating rates, cooling rates, non-equilibrium cooling rates result in development of internal stresses or residual stresses in a steel component, and this generally happens during processes like welding, casting, or even in some heat treatment processes. If you do very fast cooling, like in the case of hardening, when you quench a steel, definitely internal stresses will get developed in the material, and the reason for their development is lack of diffusion. Diffusion is not able to complete because it was diffusion whose responsibility was to get these stresses eliminated. No external load, there should be no loading. But if you resorted to non-uniform heating rates, non-uniform cooling rates, faster cooling rates, some stresses will get trapped into the material and you'll say it has got internal stresses. And what are the ill effects? Means why are we so worried if internal stresses are present in a material? See, you would have heard in several news that some catastrophic failure of a fridge occurred, of a ship occurred, not fridge, sorry, of a ship. Means all of a sudden the structure failed, some bridge collapsed. There was no vehicle passing over it, there was no external load being applied over it, but it catastrophically failed, showed failure, is because of the presence of internal stresses. So generally, whenever a structure shows sudden failure, catastrophic failure without giving you any warnings, it is because of the presence of internal stresses in the material of which the structure was fabricated. Whenever internal stresses are present, see, this is the ultimate effect. But if we break it down into other small things, see students, there is a failure mechanism which is called stress corrosion cracking. Now, as the name only tells you, what is this phenomenon? This is a phenomenon where a material would fail if an external force is applied on it, which leads to some stress in it, and also the material is placed in a corrosive environment. So stress corrosion cracking is a failure mechanism. When does a material fail because of this mechanism? When there is both some stress and a corrosive environment acting on the material simultaneously. But because suppose you have a component which is not a normal component, it is containing some internal stresses over it. So if a component is already containing some stresses in it, which are called residual or internal stresses, just when it is placed in a corrosive environment without any external load or stress being applied externally, material might fail because of stress corrosion cracking, right? Then there is something called dimensional stability. Dimensional stability means a component remains of the same dimensions until and unless some external force, external stress acts on it. But if a material is already having some internal stresses in it, it will show what is called warpage. If these dimensions would change without any external stimulus being given, and so it will start showing dimensional instability. Why is this warpage or dimensional instability taking place? Because of the presence of internal stresses in the material. Similarly, students, suppose a normal material which is not containing any residual stresses, internal stresses in it, it fails under some load. You will see that material fails under much lower a load or even under no load conditions. Why? Because it was containing internal stresses in it. Also, it is seen that if a material is containing internal stresses in it, its fatigue life, its endurance limit would also come down significantly. So having talked about all these effects of the presence of ill effects of the presence of internal stresses in steel components, it is always wise that if you detect that there are certain internal stresses present in my material, it must be eliminated. And as I said earlier, if internal stresses are present and that's the only problem with your steel component, a very good process that will come to your rescue is called stress relieving annealing. And essentially, students, this process is a subcritical process. Subcritical process, what does that mean? That means, sir, in this process the heat treatment temperature would be lower than even the lower critical temperature of the steel. So no phase transformations will take place. We know that our components are containing residual stresses because of non-uniform heating, non-uniform cooling, non-equilibrium cooling. Lack of diffusion has occurred because of all this. Diffusion process was not able to get completed when heating or cooling was being done, and that trapped these internal stresses into the material. So what we have to do is, we do not require any phase change. We do not require austenite to come and to transform that austenite into some other phases. That's not the problem. The problem is that we want some thermally activated phenomenon to come into picture, like recovery, recrystallization, diffusion. Right, largely here we require diffusion to happen in the process, but under controlled heating and controlled cooling. So what is the procedure for stress relieving annealing? Let us see. So here is the time temperature plot which is showing what needs to be done. You take the steel components which are having the problem of presence of residual stresses in them at the room temperature conditions. Now they have to be heated in a very controlled manner, students. The heating rate has to be any constant heating rate in this range. You can be a little, you can choose any heating rate between 100 to 150 degrees centigrade per hour. This would generally depend upon what amount of internal stresses are present. If they are too high, too large in magnitude, the internal stresses, please choose a lower heating rate. But in case the amount of stresses are less, then you can probably choose a slightly higher heating rate, but the heating rate has to be in this range. And to what temperature do you have to go? Means what would be the heat treatment temperature? Generally we take any temperature where diffusion process can take place actively. And for most of the steels, if you are at about 650 degrees centigrade with a reasonable holding, ample of diffusion would occur in the steel component and would eliminate any internal stresses. So we start heating the steel from the room temperature with a constant heating rate, anything between 100 to 150 degrees centigrade per hour. We go till the heat treatment temperature about 650 degrees centigrade. Now what amount of holding has to be done? That depends upon how big or small the component is. Depending upon 1 mm thickness of the cross section or the diameter, 3 to 4 minutes of holding has to be given. So if you have a component coming to you for stress relieving annealing and its cross section is about 2 mm thick, 4 to 8 minutes of holding should be given at the heat treatment temperature. No sooner this holding, stipulated holding is complete, very carefully controlled cooling has to be done with cooling rates in the range of 50 to 100 degrees centigrade per hour. Mind it, you can, if you do still non-uniform cooling, or here you had done non-uniform heating, internal stresses rather than getting eliminated will grow in number, will grow in magnitude. So controlled heating, controlled cooling is the most important point that has to be kept in mind. We have to be mindful of that. So we have to follow this slow controlled uniform constant cooling rate and follow it till a temperature of 300 degrees centigrade. when your component reaches this low a temperature, diffusion is almost complete. Now you can resort to faster cooling, you can do air cooling, and then you reach the room temperature. By this time, diffusion would have completed. All internal stresses would have got eliminated from your steel component. So I have discussed this is a subcritical process. I also said that uniform heating, uniform cooling is of utmost importance, right? Okay, so we have finished, students, with the annealing processes. In the next online class, we'll start with a very popularly used heat treatment process in the industry, which is called normalizing. Thank you so much for watching. Thank you.